Let's start, guys. Okay, so we're going to continue talking about games today. Just a quick announcement, the project proposals are due today. I think you all know that. All right, so let's tomorrow. You're right, tomorrow. Just checking. Yeah, today is not Thursday. Yeah, tomorrow. For a second, I thought it's Thursday. All right, so let's talk about games. So we started talking about games last time. We formalized them. We talked about zero-sum two-player games that were turn-taking, right? And we talked about a bunch of different strategies to solve them, like the minimax strategy or the expecting max strategy. And today we want to talk a little bit about learning in the setting of games. So what does learning mean? How do we learn those evaluation functions that we talked about? And then towards the end of the lecture, we want to talk a little bit about variations of the games we have talked about. So how about the cases where we have simultaneous games or non-zero-sum games? So that's the plan for today. So I'm going to start with a question that we're actually going to talk about it towards the end of the lecture, but it's a good motivation. So think about a setting where we have a simultaneous two-player zero-sum game. So it's a two-player zero-sum game similar to the games we talked about last time, but it is simultaneous. So you're not taking turns, you're playing at the same time. And an example of that is rock, paper, scissors. So can you still be optimal if you reveal your strategy? So let's say you're playing with someone. If you tell them what your strategy is, can you still be optimal? That's the question.
Small enough game space where they know exactly what you're going to play, you won't be successful. But for a zero-sum real-time simultaneous game of a larger scale, I think you could still be successful if that approach is like superior to the other approach taken.
So it's not. So the answer was about the size of the game. So rock, paper, scissors being small versus not being small. So the question is more of a motivating thing. We'll talk about this in a lot of details towards the end of the class. It's actually not the size that matters. It's the type of strategy that you play that matters, just to give you an idea. But like the reason that we have put this, I guess, at the beginning of the lecture is intuitively, when you think about this, you might say, no, I'm not going to tell you what my strategy is, right? Because if I say I'm going to play like scissors, you'll know what to play. But this has an intuitive answer that we're going to talk about towards the end of the lecture. So just more of a motivating example. Don't think about it too hard. All right, so let's do a quick review of games. So last time we talked about having an agent and opponent playing against each other. So and we were playing for the agent, and the agent was trying to maximize their utility. So they were trying to get this utility. The example we looked at was agent is going to pick bucket A, bucket B, or bucket C, and then the opponent is going to pick a number from these buckets. They can either pick minus 50 or 50, 1 or 3, or minus 5 or 15. And then if you want to maximize your utility as an agent, then you can potentially think that your opponent is trying to minimize your utility, and you can have this minimax game kind of playing against each other, and based on that, decide what to do. So we had this minimax tree, and based on that, the utilities that are going to pop up are minus 50, 1, and minus 5. So if your goal is to maximize your utility, you're going to pick bucket B, the second bucket, because that's the best thing you can do, assuming your opponent is a minimizer. So that was kind of the setup that we started looking at. And the way we thought about solving this game was by writing a recurrence. So we had this value, this V, which was the value of a minimax at state S. And if you're at the utility, if you're at an end state, we're going to get utility of S, right? Like if we get to the end state, we get the utility, because we get the utility only at the very end of the game. And if the agent is playing, the recurrence is maximize V of the successor states. And if the opponent is playing, we want to minimize the value of the successor states. And so that was the recurrence we started with. And we looked at games that were kind of large, like the game of chess. And if you think about the game of chess, the branching factor is huge. The depth is really large. It's not practical to do the recurrence. So we started talking about ways for speeding things up. And one way to speed things up was this idea of using an evaluation function. So do the recurrence, but only do it until some depth. So don't go over the full tree. Just do it until some depth. And then after that, just call an evaluation function. And hopefully your evaluation function, which is kind of this weak estimate of your value, is going to work well and give you an idea of what to do next. Okay? So instead of the usual recurrence, what we did was we decided to add this d here, this d right here, which is the depth that until which we are exploring, and then we decrease the value of depth after an agent and opponent plays, and then when depth is equal to 0, we just call an evaluation function. So intuitively, if you're playing chess, for example, you might think a few steps ahead, and when you think a few steps ahead, you might think about how the board looks like and kind of evaluate that based on the features that board has, and based on that, you might decide to take various actions. So similar type of idea. And then the question was, well, how are we going to come up with this evaluation function? Like, where is this evaluation function coming from? And then one idea that we talked about last time was it can be handcrafted. The designer can come in and sit down and figure out what is a good evaluation function. So in the game of chess, the example is you have this evaluation function that can depend on the number of pieces you have, the mobility of your pieces, maybe the safety of your king, central control, all these various things that you might care about. So the difference between the number of queens that you have and your opponent's number of queens, these are things, these are features that you care about. And potentially a designer can come in and say, well, I care about 9 times more than I care about how many pawns I have. So you can actually hand design these things and write down these weights about how much you care about these features. Okay? So I'm using terminology from the learning lecture, right? I'm saying we have weights here and we have features here, and someone can come and just handcraft that. Okay? Well, one other thing we can do is instead of handcrafting it, we could actually try to learn this evaluation function. So we can still handcraft the features, right? We can still say, well, I care about the number of kings and queens and these sort of things that I have, but I don't know how much I care about them. And I actually want to learn that evaluation function, like what the weights should be. Okay? So to do that, I can write my evaluation function, eval of s, as this v, as a function of state, parameterized by weights w's. And my goal is to figure out what these w's, what these weights are, and ideally I want to learn that from some data. Okay, so we're going to talk about how learning is applied to these game settings, and specifically the way we are using learning for these game settings is to just get a better sense of what this evaluation function should be from some data. Okay? So the questions you might have right now is, well, how does v look like? Where does my data come from? Because if you know where your data comes from and where your v is, then all you need to do is to come up with a learning algorithm that takes your data and tries to figure out what your v is. So we're going to talk about that at the first part of the lecture. Okay? And that kind of introduces to this temporal difference learning, which we're going to discuss in a second. It's very similar to Q learning. And then towards the end of the class, we'll talk about simultaneous games and non-zero-sum games. Okay? All right. So let's start with this v function. I just said, well, this v function could be parameterized by a set of weights, a set of w's. And the simplest form of this v function is to just write it as a linear classifier, as a linear function of a set of features, w's times v's. And these v's are the features that are hand-coded, and someone writes them, and then I just want to figure out what w's are. So this is the simplest form. But in general, this v function doesn't need to be a linear classifier. It can actually be any supervised learning model that we have discussed in the first few lectures. It can be a neural network. It can be anything even more complicated than neural network that just does regression. So we can basically, any model you could use in supervised learning could be placed here as this v function. So all I'm doing is I'm writing this v function as a function of state and a bunch of parameters. Those parameters, in the case of linear classifier, they're just w's. And in the case of the neural network, there are w's and these v's in this case of like one layer neural network. Or multi-layer. Yeah, one layer. All right, so let's look at an example. So let's think about an example, and I'm going to focus on the linear classifier way of looking at this just for simplicity. So, okay, let's pick a game. So we're going to look at Backgammon. So this is a very old game. It's a 2-player game. The way it works is you have the red player and you have the white player, and each one of them have these pieces. And what they want to do is they want to move all their pieces from one side of the board to the other side of the board. It's a game of chance. You can actually like roll 2 dice, and based on the outcome of your dice, you move your pieces various amounts to various columns. There are a bunch of rules. So your goal is to get all your pieces off the board. But if you have only like one piece and your opponent like gets on top of you, they can push you to the bar and you have to like start again. There are a bunch of rules about it. Read about it on Wikipedia if you're interested. But we're going to look at a simplified version of it. So in the simplified version, I have player O and player X, and I only have 4 columns. I have columns 0, 1, 2, and 3. And in this case, I have 4 of each one of these players, and the idea is we want to come up with features that we would care about in this game of backgammon. So what are some features that you think might be useful? Remember the learning lecture? How do we come up with like feature templates?
We try to distill down like the core components of the state. So maybe like the location of the X's and the O's, the number of them.
Yeah. Yeah, so like one idea is we have all these knowledge about the board, so maybe we should like care about the location of the X's, maybe we should care about like where the O's are, how many pieces are on the board, how many pieces are off the board. So similar type of way that we would come up with features in the first few lectures, we would do the same thing. So a feature template, set of feature templates could look like this, like number of X's or O's in column, whatever column, being equal to some value, or a number of X's or O's on the bar, maybe fraction of X's or O's that are removed, whose turn it is. So these are all like potential features that we could use. So for this particular board, here are what those features would look like. So if you look at number of O's in column 0 equal to 1, that's equal to 1. Remember, we were using these indicator functions to be more general. So like here, again, we are using these indicator functions. You might ask number of O's on a bar, that's equal to 1. Fraction of O's that are removed. So I have 4 pieces. 2 of them are already removed, so that's 1/2. Number of X's in column 1 equal to 1, that's 1. Number of X's in columns 3 equal to 3, that's 1. It's O's turn, so that's equal to 1. Okay? So we have a bunch of features. These features kind of explain what this board looks like or how good this board is. And what we want to do is we want to figure out what are the weights that we should put for each one of these features and how much we should care about each one of these features. So that is the goal of learning here. All right, so that was my model, right? So far I've talked about this V S of W. I've defined it as a linear predictor, W's times features. And now the question is, where do I get data? Because if I'm doing learning, I got to get data from somewhere. So one idea that we can use here is we can try to generate data based on our current policy, pi agent or pi opponent, which is based on our current estimate of what V is. Right? So currently, I might have some idea of what this V function is. It might be a very bad idea of what V is, but that's okay. I can just start with that. And starting with that V function that I currently have, what I can do is I can call argmax of V over successors of S and A to get a policy for my agent. Remember, this was how we were getting policy in a minimax setting. Policy for the opponent is just argmin of that V function. And then when I call these policies, I get a bunch of actions. I get a sequence of like states based on how we are following these policies, and that is some data that I can actually go over and try to make my V better and better. So that's kind of how we do it. We call these policies, we get a bunch of episodes, we go over them to make things better and better. So that's kind of the key idea. One question you might have at this point is this deterministic or not? Like, do I need to do something like epsilon greedy? So in general, you would need to do something like epsilon greedy, but in this particular case, you don't really need to do that because we have this die that we are actually rolling the dice, and by rolling the dice, we are getting different random paths that we might take. So that might take us to different states. So we kind of already have this element of randomness here that does some of the exploration for us.
You just mean like an explore probability?
Yes. Okay. So by epsilon greedy, what I mean here is, do I need to do extra exploration? Am I going to get stuck like in a particular set of states if I don't do exploration? And in this particular case, because we have this randomness, we don't really need to do that. In general, you might imagine having some sort of epsilon greedy to take us explore a little bit more. Okay, so then we generate episodes, and then from these episodes, we want to learn. Okay? These episodes look like state, action, reward, states, and then they keep going until like we get a full episode. One thing to notice here is the reward is going to be 0 throughout the episode until the very end of the game, right? Like until we end the episode, and we might get some reward at that point, or we might not. But the reward throughout is going to be equal to 0 because we are playing a game, right? Like we are not getting any rewards at the game. And if you think about each one of these small pieces of experience, S, A, R, S prime, we can try to learn something from each one of these pieces of experience. Okay? So what you have is, you actually go on board maybe. What you have here is you have a piece of experience. Let's call it S A, you get some reward, maybe it is 0, that's fine if it is 0. And you go to some S prime through that. So maybe S, take an action, you get a reward, maybe you get a reward. You go to some S prime from that. And you have some prediction, right? Your prediction is your current, V function. So your prediction is going to be this V function at the state S, parameterized with W, and this is what you already, you kind of know right now. This is your current estimate of what V is. And this is your prediction. I'm writing the prediction as a function of W, right? Because it depends on W. And then we have a target that we're trying to get to. And my target, which kind of acts as a label, is going to be equal to my reward, the reward that I'm getting. So it's kind of so if you look at this V of S and W, well, that's kind of close-ish to reward plus, I'm going to write discount factor, V of S prime W. Right? So my target, the thing that I'm trying to get to, is the reward plus gamma V of S prime W. So we're playing games. In games, gamma is usually 1. I'm going to keep it here for now, but I'm going to drop it at some point, so we don't need to really worry about gamma. And then one other thing to notice here is I'm not writing target as a function of W, because target acts kind of like my label, right? If I'm trying to do regression here, target is my label. It's kind of the ground truth thing that I'm trying to get to. So I'm going to treat my target as just like a value. I'm not writing it as a function of W. All right, so what do we try to do usually, when we are trying to do learning? We have a prediction, we have a target. What do I do? Minimize the error. So what is the error? So I can write my error as potentially a squared error. So I'm going to write 1/2 of prediction of W minus target squared. This is my squared error. I want to minimize that. So with respect to W. How do I do that? I can take the gradient. What is the gradient equal to? This is simple, right? 2 gets canceled. Gradient is just this guy, prediction of W minus target times the gradient of this inner expression. The gradient of this inner expression with respect to W is the gradient of prediction with respect to W minus 0, because target is, I'm treating it as a number. Okay. Let me move this up. So now I have the gradient. What algorithm should I use? I can use gradient descent, right? So I'm going to update my W. How do I update it? I'm going to move in the negative direction of my gradient using some learning rate eta times my gradient. My gradient is prediction of W minus target times gradient of prediction of W. All right, so that's actually what's on the slide. So the objective function is prediction minus target squared. Gradient, we just took that. It's prediction minus target times gradient of prediction. And then the update is just this particular update where we move in the negative direction of the gradient. This is what you guys have seen already. Okay. All right, so far so good. So this is the TD learning algorithm. This is all it does. So temporal difference learning, what it does is it picks these pieces of experience, S, A, R, S prime, and then based on that pieces of experience, it just updates W based on this gradient descent update, difference between prediction and target times the gradient of V. Okay. So what happens if I have this linear function? Maybe let me write this in the case that I have a linear function. So what if my V of SW is just equal to W dot phi of S? Phi of S. So what happens to my update? Minus eta. What is prediction? W dot phi of S. Right? W dot phi of S. What is target? Did you find it up there? It's the reward you're getting, the immediate reward you're getting, plus gamma times v of s prime w, which is w dot phi of s prime, times gradient of your prediction, which is what, phi of s. Okay, so I just wrote up this in the case of a linear predictor. Yes?
Q-learning, what are the differences between the two?
Yeah, so this is very similar to Q-learning. There are very minor differences that we'll talk about actually at the end of this section, comparing it to Q-learning. All right, so I want to go over an example. It's kind of like a tedious example, but I think it helps going over that and kind of seeing why it works, especially in the case that the reward is just equal to 0, like throughout an episode. So it kind of feels funny to use this algorithm and make it work, but it works. So I want to just go over like one example of this. So I'm going to show you one episode starting from S1 to some other state. And I have an episode. I start from some state. I get some features of that state. Again, these features are by just evaluating those hand-coded features. And I'm just going to start. What W should I start with? 0. Let me just initialize W to be equal to 0. Okay. Right? How do I update my W? Maybe let me just write it in this. So this is, I want to write it in a simpler, not a simpler form, but just another form. So W, the way we are updating it is the previous W minus eta times prediction minus target. I'm going to use P and T for prediction minus target times phi of S. This is the update you're doing, okay? Yeah, that's right. Okay. So what is my prediction? What is my prediction? W dot phi of S, 0. What is my target? So for my target, I need to know what state I'm ending up at. I'm going to end up at 1, 0 in this episode, and I'm going to get a reward of 0. So what is my target? My target is reward, which is 0, plus W times phi of S prime. That is 0, because W is equal to 0. So my target is equal to 0. My P minus T is equal to 0. So P minus T is equal to 0. This whole thing is 0. W stays the same. So in the next kind of step, W is just 0. Okay? I'm going to move forward. So what is prediction here? 0 times 0. Prediction is 0. What is target? I haven't, yeah, it's 0 because I haven't got any reward yet. Where do I end up at? I end up at 1, 2. So, yeah, so target is going to be a reward, which is 0, plus 0 times whatever state of phi of S prime that I'm at. So that's equal to 0. P minus T is equal to 0. It's kind of boring. So at this point, W hasn't changed. W is equal to 0. What is my prediction? Prediction is equal to 0. It's great. What is target equal to? So I'm going to end up in an end state where I get 1, 0, and I get a reward of 1. So this is the first time I'm getting a reward. What should my target be? My target is reward 1 plus 0 times 1, 0, which is 0. So my target is 1. So what this tells me is I'm predicting 0, but my target is 1. So I need to push my W's a little bit up to actually address the fact that this is equal to 1. So P minus T is equal to minus 1. So I need to do an update. Maybe I'll do that update here. So how am I updating it? So I'm doing, starting from 0, 0, minus, my eta is 0.5. That's what I allowed it, like I defined it to be. My prediction minus target is minus 1. What is phi of S? Phi of S is 1, 2. Right? So what should my new W be? What is that equal to? 0.5 and then 1. Right, so I'm just doing arithmetic here. So my new W is going to become 0.5 and 1 at the end of this one episode. So I just did one episode, one full episode, where W's were 0 throughout. And then at the very end, when I got a reward, then I updated my W because I realized that my prediction and target were not the same thing. Okay? So now I'm gonna start a new episode, and the new episode I'm starting is going to start with this particular W. And in the new episode, even though the rewards are going to be 0 throughout, so like we're actually going to update our W's. Next question.
If you, two questions. If you initialize your weights to not be zeros, would you update throughout instead of just at the end?
Yeah.
Okay. And the second question is, So S4 and S9 have the same feature vector, but you said S4 is an end state, S4.
This is a made-up example, so don't think about this example too much.
Well, is it like possible to have an end state and a non-end state have the same feature vector, or no? If you have the same feature vector, you have the same state?
It is possible to have, both of the states to have the same features, right? You could have like a setup, Depends on what sort of feature. You could use like really not representative features. Like if you really want S4 and S9 to differentiate between them, you should pick features that differentiates between them. But if they're kind of the same and have the same sort of characteristics, it's fine to have a feature that gives the same value.
If right before we get to the reward, the phi of x or the feature vector has one entry that's always decimal, like instead of 1, 2, you have 1, 0 leading to the final state, then the weight corresponding to that
is going to, it will never converge. And that kind of tells you that that entry in your feature vector, you don't care about that, right? It's always like, it's always staying the same. And if it is always 0, it doesn't matter like what the weight of that entry is. So in general, you want to have features that are differentiating and you're using it in some way. So for the second row, I'm not gonna write it up because that takes time. So let's start with a new episode. We start with S1 again, but now I'm starting with this new W that I have. So I can compute the prediction is 1. I can compute my target, it's 0.5. And what we realize here is we overshoot it. So before prediction was 0, target was 1, we were undershooting. We fixed our W's, but now we're overshooting. So we need to fix that.
Clarification on the relationship between the features and the weights. They always have to be the same dimension. And what should we be thinking about that would make a good feature for updating the weights specifically?
So first off, yes, they need to be always in the same dimension because you're doing this dot product between them. The feature selection, you don't necessarily think of it as like, how am I updating the weights? You think of the feature selection as, is it representative of how good my board is? Is it, for example, in the case of backgammon? Or is it representative of how good I'm navigating? So it should be a representation of how good your state is. And then it's usually like hand designed, right? So it's not necessarily, you shouldn't think of it as how is it helping my weights. You should think of it as how is it representing how good my state is.
For the blackjack example, if you have a threshold of 21 and then you have a threshold of 10, if you're using the same feature extraction for both, how does that affect the generalizability of the model, the agent?
Yeah, so you might choose two different features and one of them might be more like, so there is kind of a trade-off, right? You might get a feature that actually differentiates between different states very well, but then that makes learning longer, that makes it not as generalizable. And then on the other hand, you might get a feature that's pretty generalizable, but then it might not do these specific things that you would want to do or these differentiating factors about it. So picking features, it's an art, right? So, all right. So let me move forward because we have a bunch of things coming up. Okay. So I'll go over this real quick then. So we have the W's, right? So we now update the W based on this new value. And kind of similar thing, you have a prediction, you have a target, you're still overshooting, so you still need to update it. And then once you update it to 0.25 and 0.75, then it kind of stays there and you're happy. Okay? All right, so this was just an example of TD learning, but this is the update that you have kind of already seen, right? And then a lot of you have pointed out that this is similar to Q learning already, right? This is actually pretty similar. The update is very similar. Like we have these gradients in the same way that we have in Q learning. And we are looking at the difference between prediction and target, same way that we are looking at in Q learning. But there are some minor differences. So the first difference here is that Q learning operates on the Q function. A Q function is a function over state and actions. Here we are operating on a value function, right, on V, and V is only a function of state, right? And part of that is actually because in the setting of a game, we already know the rules of the game, so we kind of already know the actions. We don't need to worry about it as much, the same way that we are worrying about it in Q learning. The second difference is Q learning is an off-policy algorithm. So the value is based on this estimate of the optimal policy, which is this Q opt, right? It's based on this optimal policy. But in the case of TD learning, it's an on policy. The value is based on this exploration policy, which is based on a fixed pi. And sure, you're updating the pi, but you're going with whatever pi you have and kind of running with that and keep updating it. Okay, so that's another difference. And then finally, like in Q-learning, you don't need to know the MDP transitions, so you don't need to know this transition function as transition from SA to S prime. But in the case of TD learning, you need to know the rules of the game. So you need to know how the successor function of S and A works. Okay? So those are some kind of minor differences, but from like a perspective of like how the update works, it is pretty similar to what Q-learning does. Okay? All right, so that was kind of this idea of I have this evaluation function, I want to learn it from data, I'm going to generate data. From that generated data, I'm going to update my W's. So that's what we've been talking about so far. And the idea of learning, using learning to play games is not a new idea, actually. So in 50s, Samuels looked at a checkers game program, so where he was using ideas from self-play and ideas from like similar type of things we have talked about, using really smart features, using linear evaluation functions to try to solve the checkers program. So a bunch of other things that he did included adding intermediate rewards. So kind of throughout, like to get to the endpoint, he added some intermediate rewards, used alpha-beta pruning and some search heuristics. And it was kind of impressive, like what he did in 50s. Like he ended up having this game that was playing, like I was reaching like human amateur level of play, and he only used like 9K of memory, which is like really impressive if you think about it. So this idea of learning in games is old. People have been using it. In the case of backgammon, this was around the 90s when Tesoro came up with an algorithm to solve the game of backgammon. So he specifically used this TD lambda algorithm, which is similar to the TD learning that we have talked about. It has this lambda temperature parameter that kind of tells us how good states are, like as they get far from the reward. He didn't have any intermediate rewards. He used really dumb features, but then he used neural networks, which was kind of cool. And he was able to reach human expert play and kind of gave us, and this kind of gave us some insights into how to play games and how to solve like these really difficult problems. And then more recently, we have been looking at the game of Go. So in 2016, we had AlphaGo, which was using a lot of expert knowledge in addition to ideas from Monte Carlo tree search. And then in 2017, we had AlphaGo 0, which wasn't using even expert knowledge. It was all like based on self-play. It was using dumb features, neural networks, and then basically the main idea was using Monte Carlo tree search to try to solve this really challenging, difficult problem. So I think in this section, we're going to talk a little bit about AlphaGo 0 too. So if you're attending section, I think that will be part of the story. All right, so the summary so far is we have been talking about parameterizing these evaluation functions using features. And the idea of TD learning is to look at this error between our prediction and our target and try to minimize that error and find better W's as we go through. So, all right, so that was learning in games. So now I want to spend a little bit of time talking about other variations of games. So the setting where we take our games to simultaneous games from turn-based, and then the setting where we go from zero-sum to non-zero-sum. All right. Okay, simultaneous games. So, all right. So far we have talked about turn-based games like chess, where you play and then the next player plays, and you play and next player plays. And minimax strategies seem to be pretty okay when it comes to solving these turn-based games. But not all games are turn-based, right? Like an example of it is rock, paper, scissors. You're all playing at the same time. Everyone is playing simultaneously. The question is, how do we go about solving a simultaneous game? Okay? So let's start with a game that is a simplified version of rock, paper, scissors. This is called a two-finger Mora game. So the way it works is we have two players, player A and player B, and each player is going to show either one finger or two fingers, and then you're playing at the same time. And the way it works is if both of the players show 1 at the same time, then player B gives $2 to player A. If both of you show 2 at the same time, player B gives player A $4. And then if you show different numbers, like 1 or 2 or 2 or 1, then player A has to give $3 to player B. Okay? Does that make sense? So can you guys talk to your neighbors and play this game real quick? Played once. Okay. All right. So what was the outcome? How many of you were in the case where A chose 1 and B chose 1? Oh yeah, 1. Okay, 1 per here. A chose 1, B chose 2. 1 per there. Is it like 4 people played? So A chose 2, B chose 1. You have, okay, 2 pairs. And then 2 and 2. All right, so you can kind of see like a whole mix of strategies here happening. And this is the game that we're going to talk about a little bit and think about what would be a good strategy to use when you're solving this simultaneous game. Okay? All right, so let's formalize this. We have player A and player B. We have these possible actions of showing 1 or 2. And then we're going to use this payoff matrix, which represents A's utility if A chooses action A and B chooses action B. So before we had this value function, right? Before we had this value function over our state here, now we have this value function that is, maybe should I use here? Yeah, I'll just use here. That is again from the perspective of agent A. So remember, like before when we were thinking about value function, we were looking at it from the perspective of the first player, the maximizer player, the agent. Now I'm looking at all of these games from the perspective of A player. So I'm trying to like get good things for A. That's my goal.
In this case, it's not at the end like it was before, but it's throughout.
Yeah, and then this is like a one-step game too, right? So like you're just playing and then you see what you get. So we're not talking about repeated games here. So you're playing. See what happens. Okay, so we have this V, which is V of A and B, and this basically represents A's utility if agent A plays A and if agent B plays B. Okay, and this is called, and you can represent this with a matrix, and that's why it's called a payoff matrix. I'm going to write that payoff matrix here. So payoff matrix, I'm going to write A here, B here. Agent A can show 1 or can show 2. Agent B can show 1 or can show 2, right? If both of us show 1 at the same time, agent A gets $2. If both of us show 2 at the same time, agent A gets $4. Otherwise, agent A has to pay, so agent A gets minus $3. And again, the reason I only like talk about one V is we are still in the setting of zero-sum games, so whatever V agent A gets, agent B gets negative of that, right? So if agent A gets $4, agent B is paying minus $4. So I'm just writing one V from perspective of agent A. And this is called the payoff matrix. Okay. All right, so now we need to talk about what does a solution mean in this setting. So what is a policy in this setting? And the way we refer to them in this case are as strategies. So we have pure strategy, which is almost like the same thing as deterministic policies. So a pure strategy is just a single action that you decide to take. So you have things like pure strategies. The difference between pure strategy and deterministic policy is, if you remember, deterministic policy, again, is a function of state, right? So it's a policy as a function of state. It gives you an action. Here we have like a one-move game, right? So it's just that one action. And we call it pure strategy. We have also this other thing that's called mixed strategy, which is equivalent to stochastic policies. And what a mixed strategy is a probability distribution that tells you what's the probability of you choosing A. So pure strategies are just actions, A's. And then you can have things that are called mixed strategies, and they are probabilities of choosing action A. Okay? All right. So here is an example. So if you say, well, I'm going to show you 1, I'm going to always show you 1, then if you can write that strategy as a pure strategy that says, I'm going to always, with probability 1, show you 1, and with probability 0, show you 2. So let's say the first column is for showing 1, the second column is for showing 2. So this is a pure strategy that says, always I'm going to show you 1. If I tell you, well, I'm going to show you 2, then I can write that strategy like this, right? With probability 1, I'm always showing you 2. I could also come up with a mixed strategy. Mixed strategy would be, I'm going to flip a coin, And if I get 1/2, I'm going to give you, if I get heads, I'm going to show you 1. If I get tails, I'm going to show you 2. And then you can write that as this, and this is going to be a mixed strategy. You could totally play that too. If you're in this simultaneous game, you could just bring chance in and be like, half the time I'm going to show you 1, half the time I'm going to show you 2 based on chance. Everyone happy with mixed strategies and your strategies? All right, so how do we evaluate a value of a game? So remember in previous lecture and like in the MDP lecture even, we were talking about evaluating. If someone gives me the policy, how do I evaluate how good that is? So the way we are evaluating that is again by this value function v, and we are gonna write this value function as a function of pi a and pi b. Maybe I'll just write that up here, or I'm gonna erase this because this is repetitive. So I'm gonna say a value of agent A following pi A and agent B following pi B. What is that equal to? Well, that is going to be the setting where pi A chooses action A, pi B chooses action B, times value of choice A and B, summing over all possible A and B's. Okay, so let's look at an actual example for this. So for this particular case of two-finger Mora game, let's say someone comes in and says, I'm going to tell you what pi A is. Policy of agent A is just to always show 1. And policy of agent B is this mixed strategy, which is half the time show 1, half the time show 2. And the question is, what is the value of these two policies? How do we compute that? Well, I'm going to use my payoff matrix, right? So 1 times 1 over 2 times the value that we get at 1, 1, which is equal to 2. So it's 1 times 1 over 2 times 2, plus 0 times 1 over 2 times 4, plus 1 times 1 over 2 times minus 3. The value that I get is minus 3, plus 0 times 1 over 2 times minus 3. Okay. And, well, what is that equal to? What is that equal to? There are 2 zeros here, that's minus 1 over 2. Okay, so I just computed that the value of these two policies is going to be minus 1 over 2. And again, this is from perspective of agent A, and it kind of makes sense, right? If agent A tells you I'm going to always show you 1, then probably agent 2 is following this mixed strategy. Agent A is probably losing, and agent A is losing minus 1 over 2 based on this strategy.
This is in the simplified case where we only have this one state and then we put it in the state right away.
We only have one state.
So it's we only take one action in this environment. So we have one state and we take one action and it's automatically that state. If we had more than one state, would we have that for every single?
So that opens up a whole set of new questions that you're not discussing in this class. So that introduces repeated games. So you might be interested in looking at what happens in repeated games. In this class right now, we're just talking about this one step, one play. We're playing like zero-sum game. We're playing like, let's say, rock, paper, scissors, and you just play once. Like you might say, oh, what happens if you play like 10 times? Then you're building some relationship and weird things can happen. And so that introduces a whole new class of games that we're not talking about. All right, so the value is equal to minus 1 over 2. Okay. All right, so that was a game value. So we just evaluated it, right? If someone tells me it's pi A and pi B, I can evaluate it. I can know how good pi A and pi B is from the perspective of agent A. Okay. So what do we want to do? Like when we want to try to solve games, all we want to do is from the agent A's perspective, we want to maximize this value. I want to get as much money as possible. And this value is from my agent A perspective, so I should be trying to maximize this. Agent B should be trying to minimize this. Right? Like think minimax, right? Agent B should be minimizing this. Agent A should be maximizing this. That's what we want to do. But the challenge here is we're playing simultaneously, so we can't really use the minimax tree. Like you remember the minimax tree? Like in that setting, we had sequential plays, and then we could like wait for agent A to play, and then after that play, and that would give us a lot of information. Here we are playing simultaneously. So what should we do? Okay, so what should we do? So I'm going to assume we can play sequentially. So that's what I want to do for now. So I'm going to limit myself to pure strategies. So maybe I'll I'll come over here. So right now I'm going to focus only on pure strategies. I want to just consider a setting, very limited setting, and see what happens. And I'm going to assume, oh, what if we were to play sequentially? What would happen? How bad would it be if we were to play sequentially? So, so we have the setting where player A goes first. What do you think? Do you think like if player A goes first, is that better for player A, or is that worse for player A? Worse for player A. Okay, so that's probably what's going to happen. Try that. Okay. So player A was trying to maximize, right? This V. Player B was trying to minimize, right? And then each of them have actions of either showing 1 or showing 2. This is player A. This is A. This is agent B. We can show 1 or 2, right? If we do one, if we show 1, 1, player A gets what, $2? Is that right? Is 2 right? Let's see the board. Otherwise, player A gets -$3. If you have 2, 2, player A gets $4. Right? So, okay. So now if we have this sequential setting, if you're playing minimax, then player B is going second. Player B is going to take the minimizer here. So player B is going to be like this one. And in this case, player B is going to be like this one. What should player A do? Well, in both cases, player A is getting -$3. It doesn't actually matter. Player A could do any of them. And player A, at the end of the day, is going to get -$3. Right? And this is the case where player A goes first. What if player A goes second? Second. Okay. So then player B is going first. Player B is minimizing. And then player A is maximizing. And we have the same values here. Okay. So this is player A going second. Player A going second tries to maximize. So we'd like to pick these ones. Player B is here. Player B wants to minimize. So player B is going to be like, okay, if you're going second, I'd rather show you 1, because by showing you 1, I'm losing less. If I show you 2, I'm losing even more. So and then in that setting, we are going to get 2. So player A is going to get $2. Okay. All right. So that was kind of intuitive. If we have pure strategies, it looks like if we are going second, that should be better. Okay. So going second is no worse. It's the same or better. And then that basically can be represented by this minimax relationship, right? So agent A is trying to maximize. So in this second case, we are maximizing second over our actions of A and B, and player B is going first. So this is going to be greater than or equal to the case where player A is going first. Sorry, no, not min. That makes sense. V of A and B. So I'm going to just write these things that you're learning throughout on the side of the board, maybe up here. So what did we just learn? We learned if we have pure strategies, right, going second is better. That sounds intuitive and right. Okay. So far, so good. Okay? So the question that I want to try to think about right now is, what if we have mixed strategies? What's going to happen if we have mixed strategies? Are we going to get the same thing? Like if you have mixed strategies, is going second better? Or is it worse? Or is it the same? So that's the question to try to answer. Okay? So let's say player A comes in, and player A says, well, I'm going to reveal my strategy to you. What I'm going to do is I'm going to flip a coin. Depending on what it comes, I'm either going to show you 1 or I'm going to show you 2. That's what I'm going to tell you. That's what I'm going to do. Okay? So what would be the value of the game under that setting? So the value of the game would be, maybe I'll write it here. So the value of pi A and pi B pi A is already this mixed strategy of 1/2, 1/2, right? Is going to be equal to pi, is this, yeah, actually, all right, so what is that going to be equal to? It's going to be pi B times 1, right? So it's going to be pi B choosing 1 times 1/2, with probability 1/2, agent A is also picking 1. If it is 1, 1, we are going to get 2, right? Plus pi B choosing 1, pi A with 1/2 choosing 1, and then we're going to get minus $3. Sorry, choosing 2, we're going to get minus $3, plus pi B choosing 2 times 1/2 pi A choosing 2, we're going to get $4, plus pi B choosing 2 times pi A choosing 1, and that's minus $3. So I just like iterated all the 4 options that we can get here under the policy of pi B choosing 1 or 2, and then pi A is always just half, right? Because they're following this mixed strategy. So, well, what is this equal to? That's equal to minus 1/2 pi B of 1 plus 1/2 pi B of 2. Okay? So that's the value. Okay? So again, the setting is someone came in, agent A came in, agent A told me, I'm following this mixed strategy. This is going to be the thing I'm going to do. What should I do as an agent B? What should I do as an agent B?
You always want to take 1.
So, okay, so that was too quick. So you always should do 1. But why is that? Well, if agent A comes and tells me, well, this is the thing I want to do, I should try to minimize value of agent A, right? So what I'm really trying to do as agent B is to minimize this, right? Because I don't want agent A to get anything. So if I'm minimizing this, in some sense, I'm trying to come up with a policy that minimizes this. Pi is a probability, so it's like a positive number. I have like a positive part and a negative part here. The way to minimize this is to put as much weight as possible for this side and as little as possible for this side. So that tells me that never show 2 and always show 1. Does everyone see that? So the best thing that I can do as agent 2 is to follow a pure strategy that always shows 1 and never shows 2. Okay? So this was kind of interesting, right? Like if someone comes in and tells me, this is the thing, this is the mixed strategy I'm going to follow, I'll have a solution in response to that, and that solution is always going to be a pure strategy, actually. So that's kind of cool. All right, so this is actually what's happening in a more general case. I'm going to make a lot of generalizations in this lecture. So I show one example and I generalize it, but if you're interested in details of it, we can talk about it offline. So yeah, so the setting is for any fixed mixed strategy pi A. So pi A told me what their mixed strategy is. It's a fixed mixed strategy. What I should do as agent B is I should minimize that value. I should pick pi B in a way that minimizes that value, and that can be attained by pure strategy. So the second thing that I've learned here is if player A plays a mixed strategy, player B has an optimal pure strategy. That's kind of interesting. Right? Okay, so in this case also, we haven't decided what the policies should be yet, right? Like we've still been talking about the setting where like agent A comes in and tells us what their policy is, and we know how to respond to it. It's going to be a pure strategy. Okay? So now I want to figure out what is this policy, like what should be this mixed strategy actually. So I want to think of it more generally. So I want to go back to those 2 diagrams and actually modify those 2 diagrams in a way where we talk about it a little bit more generally. Maybe, yeah, I'll just modify these. Okay, so let's say that, okay, and I'm going to think about both of the settings. So let's say, again, player A is deciding to go first. Player A is going to follow a mixed strategy. So this is all we know. But we don't know what mixed strategy. Player A is going to decide to follow a mixed strategy. This is player A. Player A is maximizing. Player A is following a mixed strategy. The way I'm writing that mixed strategy is more generally saying player A is going to show 1 with probability P and is going to show 2 with probability 1 minus P. More generally, like some P value. Okay? And then after that, it's player B's turn. We have just seen that player B, the best thing player B can do is to do a pure strategy. So player B is either 100% is going to pick 1 or 100% is going to pick 2.
Player B could really say that both terms were the same, then player B follow a mixed strategy that would be the best strategy, even though it would get the same as any pure strategy. So, both of those terms behind on the blue on the board you wrote right there, yeah, both those terms were the same, both blue terms. Then player B could follow any kind of strategy, right?
So the thing is that the strategies are probabilities, right? So there are values from 0 to 1. And then you kind of always end up with this negative term that you're trying to make as negative as possible, and this positive term that you're trying to get as positive as possible. And that's kind of intuitively why you end up with a pure strategy. And by pure strategy, what I mean is you always end up putting as much possible, all your probabilities on the negative term and nothing on the positive term because you're trying to minimize this. So that's kind of intuitively why you're getting this pure strategy.
One half.
So you wouldn't get one. So that is what I mean. So if you wouldn't ever get 1/2 and 1/2. If you get 1/2 and 1/2, that's a mixed strategy. That's not a pure strategy. And I'm saying you wouldn't get a mixed strategy because you would always end up in this setting that to minimize this, you end up pushing all your probabilities to this negative term. All right. All right. So let me go back to this. So. All right, so we have the setting where player A goes first. Player A is following a mixed strategy with P and 1 minus P. Player B is going to follow a pure strategy, either 1 or 2. I don't know which one, right? So what's going to happen is if you have 1, 1, then that is going to give me 2, value 2, right? So it's 2 times P. I'm trying to write the value here. Am I writing it right? Is it 2 times P plus, 1 minus P times 3, right? So with probability 1 minus P, this guy is going to pick 2. If this guy picks 1, we're going to get minus 3. Okay? And then for this side, if with probability 1 minus P, A is going to show 2. If I am going to show 2, then I'm going to get 4. So it's 4 times 1 minus P. And with probability P, this guy is going to show 1. I'm going to show 2. So that is minus 3. All right, so what are these equal to? So this is equal to 5p minus 3. That is equal to minus 7p plus 4. Okay, so I'm talking about this more general case. In this more general case, player A comes in, player A is playing first, and is following a mixed strategy, but doesn't know what P they should choose. They're choosing a P and 1 minus P here. And then player B has to follow a pure strategy. That's what we decided. And then under that case, we either get 5p minus 3 and minus 7p plus 4. Okay? What should player B do here? This is player B and this min node. What should player B do? Should player B pick 1 or 2? Player B should pick a thing that minimizes between these two. Right? So player B is going to take the minimum of 5p minus 3 and minus 7p plus 4. Okay? What should player A do? What should player A do? I'm thinking minimax, right? So when you think about the minimax, player A is maximizing the value. So player A is going to maximize the value that comes up here. So player is going to maximize that. And also, I'm saying player A needs to decide what P they're picking. So they're going to pick a P that maximizes that. Is this clear? Like these computations? Yeah, so these are the 4 different things in my payoff matrix. So I'm saying is with probability P, A is going to show me 1, right? And I'm going to go down this other route where B is also choosing 1. So 1, like both of us are showing 1, then I'm going to get 2, right? So I'm going to get $2. So that's where the $2 comes from, times probability P. With probability 1 minus P, A is going to show me 2. I'm going to show 1. That's minus $3 times probability 1 minus P. So that's how, for this particular branch, I know the payoff is going to be 5P minus 3. Does that make sense? And then for this side, again, like with probability 1 minus P, A is going to show me 2. If it is both of them 2, I'm going to get $4. That's why it's 4 times probability of 1 minus P. With probability P, A is going to show me 1. So that's why I'll lose $3. That's minus 3 times probability P. So that's minus 7P. So, and then the second player, what they're going to do is they're going to minimize between these two values. They're going to pick 1 or 2. They're deciding, should I pick 1 or should I pick 2? And the way they're deciding that is by trying to pick 1 or 2 based on which one minimizes these two values. But I'm writing it like using this variable P that's not decided yet. And this variable P is the thing that player A needs to decide. So what P should player A decide? Player A should decide a P that maximizes this. So I'm writing like literally a minimax relationship here. Okay? All right, so the interesting thing here is this 5P minus 3 is some line, right, with positive slope. This is 5P minus 3. And this minus 7P plus 4 is another line, minus 7P plus 4. It's another line with negative slope. What is the minimum of these? Where is going to be the minimum of these happening? Minimum of these two lines. Where they meet each other, right? This is going to be the minimum of the two. Okay? So the P that I'm going to pick is going to be actually the P where the value of P where these two are equal to each other. And that turns out to be at, I don't know what it is, 7/12 or something. Actually, I don't know where it is. What is this value? Yeah, so it's going to happen at 7/12. And the value of it is minus 1/12. Right? So let's recap. Okay, what did I do? So I'm talking about the simultaneous game, but I'm relaxing it and making it sequential. I'm saying A is going to play first, B is playing second. The thing that's going to happen is A is playing first. A is deciding to choose a mixed strategy. So A is deciding to say maybe 1/2, 1/2. But maybe the A doesn't want to say 1/2, 1/2, wants to come up with some other probabilities. So the thing A is deciding is, should I pick 1 with probability P, and should I pick 2 with probability 1 minus P, and what should that P be? So what is the probability I should be picking 1? So that's what A is trying to decide here. Okay? So whatever A decides with P and 1 minus P ends up in two different results. And based on them, B is trying to minimize that. When B is trying to minimize that, B is minimizing between these two linear functions. These two linear functions meet at one point. That is the point that this thing is going to be minimized. And that actually corresponds to a p-value when A tries to maximize this. This is, I know, a little bit. This requires a little bit of thinking. But any clarification questions? See a lot of lost faces. So.
By having this policy, they can still be losing.
Yeah, and then the interesting point is exactly right. Yeah, so A is still, by the way, losing. So even in this case, where A is trying to come up with the best mixed strategy he could do, the best mixed strategy A is doing is show 1 with probability 7/12 and show 2 with probability 5/12. This comes from here. Even under that scenario, A is losing. A is losing minus 1/12. Okay? All right. Okay. So also, I haven't solved a simultaneous game yet, right? Like I have talked about the setting where A plays first. So what if B plays first? So I'm going to swap this. What if B plays first? So A goes second, B plays first. I'm going to modify this one now. Okay. B goes first. A is going second. B is going to reveal the strategy, his strategy. The strategy that B is going to reveal is also, again, I'm going to, with probability P, show you 1. With probability 1 minus P, show you 2. Then A plays. A is trying to maximize. And A has to play a pure strategy because of that, right? Like the best thing A can do is going to be a pure strategy. Always going to be either showing 1 or 2. And A is deciding which one, but doesn't know yet. And the values here are going to be exactly the same thing as there. So they're 5p minus 3 minus 7p plus 4. Okay? All right, so what's happening here? So in this case, A is playing second. What A likes to do is A likes to maximize between 5p minus 3 and minus 7p plus 4. That's what A likes to do. B is going B is going first. So then B has to minimize that and pick a P that minimizes that. Okay? So these two are exactly these same two lines, but now I'm picking the maximum of them. The maximum of these two lines end up being exactly the same point as before, ends up being exactly the same P as before, and giving exactly the same value as before. So this is also equal to minus 1 over 12. So what this is telling me is, if you're playing a mixed strategy, even if you reveal your best mixed strategy at the beginning, it doesn't matter. It actually doesn't matter if you're going first or second. So like in the Mora game when you were playing, if you were playing a mixed strategy and you would tell your opponent, this is the thing I'm going to do and this is a mixed strategy, actually and if it was the optimal thing, like it didn't matter if they know it or not. Like you'd still get the same value. So again, you get 5p minus 3 and minus 7p plus 4. And then now you're minimizing over maximum of these two lines. Maximum of these two lines ends up being at the same point. And you pick a P that kind of maximizes that. And you get the same value. So this is called the von Neumann's theorem. So von Neumann, like this whole thing that we just did over this one example, there's a theorem about it that says for every simultaneous two-player zero-sum game with a finite number of actions, the order of plays doesn't matter. So B is playing second or B is playing first, the values are going to be the same thing. If you're minimizing over maximum or maximizing over minimum of that value, it's going to be the same thing. Okay? So this is kind of the third thing that we just learned, which is von Neumann's theorem, which says if I'm writing a modification, a simpler, shorter version of it. So if playing mixed strategy, order of play doesn't matter. And remember, if you play mixed strategy, your opponent is going to play pure strategy, because this is the first point that we had before it. Right? If you play mixed strategy, your opponent is going to follow a pure strategy, either 1 or 2, probability 1.
Probability P, like if we're doing ordering, one of the two answers will come out, the probability P or 1, it'll be either 1 or 2, and then in that case, the second player can choose which is better, right?
So in this case, yeah. So the thing is, these two end up being equal. So the way to it doesn't matter, because the way for you to maximize this is going to be the point where the two end up being equal. So the two branches, if you actually plug in P equal to 7 over 12 here, these two values end up being equal.
Equal, right?
Not an expectation, they're actually equal. And the reason that they end up being equal is you are trying to minimize the thing that this guy is trying to maximize. So you're trying to pick the P that actually makes this thing equal. So no matter what your opponent does, you're gonna get the best thing that you can do. So yeah, think of it like this. Okay, so I'm player A. I still have a choice. My choice is to pick a P. I want to pick a P that I'm not gonna lose as much. What P should I pick? I should pick a P that makes these choices the same. Because if I pick a P that makes this one higher than this one, of course the second player is going to make me lose and then go down a route that's better for the second player. So the best thing that I can do here is make these two as equal as possible. So then the second player, whatever they choose 1 or 2, it's going to be the same thing. It's going to be, does that make sense?
I understand it's not an expectation, you're multiplying by P and 1 minus P, so you're saying if probability. Oh,
so in expectation, when you're saying when you're choosing P. Yeah, so I'm treating P as a variable that I'm deciding, right? P is the thing I got to be deciding. So I'm player A, I got to be deciding a P. That's not going to be too bad for me. Let's say I would pick a P that doesn't make these things equal. Let's say, I don't know, I would pick a P that makes this guy, 10, and this makes this guy 5. The second player is, of course, going to make me lose, and of course is going to, pick the thing that's going to be the worst thing for me. So the best thing I can do is I can like make both of them, I don't know, 7. So it's not going to be as bad. So that's kind of the idea. All right, so let me move forward because there's still a bunch of things happening. All right, so the kind of key idea here is revealing your optimal mix strategy does not hurt you, which is kind of a cool idea. The proof of that is interesting if you're interested in it. Look at the notes. You can use linear programming here. The reason, kind of the intuition behind it is if you're playing mixed strategy, the next person has to play pure strategy, and you have n possible options for that pure strategy. So that creates n constraints that you're putting in for your optimization. You end up with a single optimization with n constraints, and then you can use like linear programming duality to actually solve it. So you could compute this using linear programming, and that's kind of the 1ms theorem. So let's summarize what we have talked about so far. So we have talked about these simultaneous games, and we've talked about the setting where we have pure strategies, and we saw that if you have pure strategies, going second is better. Right? Going second is better if you're just telling you like what's the pure strategy you're using. Right? So that was kind of the first point up there. And then if you're using mixed strategies, it turns out it doesn't matter if you're going first or second. You're telling them what your best mixed strategy is, and they're going to respond based on that. So, and that's the von Neumann's minimax theorem. Okay. All right, so next 10 minutes, I want to spend a little bit of time talking about non-zero sum games. So far we have talked about zero sum games where it's either minimax, I get some reward, you get the negative of that, or vice versa. There are also these other things called collaborative games where we are just both maximizing something, so we both get like money out of it. And then that's kind of like a single optimization. It's a single maximization. You can think of it as plain search. In real life, we are kind of somewhere in between that. And I want to motivate that by an example. So I want to motivate that by this idea of prisoner's dilemma. How many of you have heard of prisoner's dilemma? Okay, good. Okay. So the idea of prisoner's dilemma is you have a prosecutor who asks A and B individually if they will testify against each other or not. Okay? If both of them testify, then both of them are sentenced to 5 years in jail. If both of them refuse, then both of them are sentenced to 1 year in jail. If one testifies, then he or she gets out for free, and then the other one gets 10 years sentence. Play with your partner real quick. All right. Okay, so let's look at the payoff matrix. So I think you kind of have an idea now of how the game works. Is that A or B? So you have two players, A or B. Each one of you have an option. You can either testify or you can refuse to testify. So B can testify and A can refuse to testify. And I'm going to create this payoff matrix. This payoff matrix is going to have 2 entries now in each one of these cells. And why is that? Because we have a non-zero sum game. Before, our payoff matrix only had 1 entry because this was for player A. Player B would just get negative of that. But now player A and B are getting different values. So if both of us testify, then both of us get 5 years jail, right? So A gets 5 years jail, B gets 5 years, right? If both of us refuse, A gets 1 year jail, B gets 1 year jail, 1 year jail. And then if it is a setting where one of us testifies, the other one refuses, one of us gets 0, the other one gets 10 years jail. So if I refuse to testify, then I get 10 years jail, right? And then B gets 0. And then in this case, A gets 0, and B gets 10. Okay? So the payoff matrix is now going to be for every player, we are going to have a payoff matrix. So now we have this V value function, which is a function of a player. For policy A and policy B will be the utility for one particular player, because you might be looking at it from perspective of different players. Okay? So the von Neumann's minimax theorem doesn't really apply here because we don't have the zero-sum game, but we actually get something a little bit weaker, and that's the idea of Nash equilibrium. So a Nash equilibrium is a set of policies pi star A and pi star B so that no player has an incentive to change their strategy. So what does that mean? So what that means is if you look at the value function from perspective of player A, value function from perspective of player A at the Nash equilibrium at pi star A and pi star B is going to be greater than or equal to value of any other policy, pi A, if you fix pi B. Okay? And at the same time, the same thing is true for value of B. So for agent B, value of B at Nash equilibrium is going to be greater than or equal to a value of B at any other pi B if pi A fixes their policy. Okay? So what does that mean in this setting? Do we have a Nash equilibrium here? So let's say I start from here. I start from A equal to minus 10, B equal to 0. Can I get this better? Can I make this better? Oh, did I flip them? I always, okay. Flipped, right? 0 minus 10? Minus 10, 0. Okay, so let's say I start from here. Can I get this better? Can I make this better? I start from this cell. A gets 0 years of jail. That's pretty good. B gets 10 years of jail. That's not that great. So B has an incentive to change that, right? Like B has an incentive to actually move in this direction. Right? So B has an incentive to get 5 years jail instead of 10 years. Similar thing here. What if you start here? A has 1 year jail, B has 1 year jail. A has an incentive to change this now and gets 0 years jail. B has an incentive to change this and gets 0 years jail. And we end up with this cell where like we don't have any incentive to change our strategy. So we have one Nash equilibrium here, and that one Nash equilibrium here is both of us are testifying and both of us are getting 5 years jail. Which is kind of interesting because there is like a socially better choice to have here, right? Like both of us, like if both of us would refuse, like we would each get 1 year jail, but that's not going to be Nash equilibrium. Okay? All right. So there's a theorem, which is Nash's existence theorem, which basically says if any finite player game with finite number of actions, if you have any finite player game with finite number of actions, then there exists at least one Nash equilibrium. And then this is usually one mixed strategy Nash equilibrium, at least one mixed strategy Nash equilibrium. In this case, it's actually a pure strategy Nash equilibrium. But in general, there exists at least one Nash equilibrium if you have a game of this form. All right, so let's look at a few other examples. Two-finger Mora. What would be the Nash equilibrium for that? So we just actually solved that's using the minimax, von Neumann's minimax theorem, right? So it would be if you're playing a mixed strategy of 7/12 and 5/12. You might kind of modify your two-finger Mora game and make it collaborative. So in a collaborative setting, what that means is we both get $2. Or we both get $4, or we both lose $3. So a collaborative two-finger Mora game, it's not a zero-sum game anymore. And you have two Nash equilibria. So you would have a setting where A and B, both of them play 1, and the value is 2, or A and B, both of them play 2, and the value is 4. And then Prisoner's Dilemma, it's the case where both of them testify. We just saw that on the board. All right. Okay, so the summary so far is we've talked about simultaneous zero-sum games. We talked about this von Neumann's minimax theorem, which has like multiple minimax strategies and a single game value, right? Like we had a single game value because it was zero-sum. But in the case of non-zero-sum games, we would have something that's slightly weaker. That's Nash's existence theorem. We would still have multiple Nash equilibria. We could have multiple Nash equilibria. But we also have multiple game values depending on whose perspective you're looking at. So this kind of was just a brief, like short introduction to game theory and econ. There's a huge literature around different types of games in game theory and economics. If you're interested in that, take classes. And yeah, there are other types of games too, like security games or resource allocation games that have some characteristics that are similar to things you have talked about. If you're interested in any of them, maybe you can take a look at them. Would be useful for projects. And with that, I'll see you guys next time.